Good morning, students. Today we will discuss about the new topic. So that is the thing about an atomic size of an atom. Right. So before studying this atomic size, we should know some concepts. So that is, for example, so the lithium and the sodium, the potassium and rubidium, the cesium and then the francium. So what about the size of atom down the group? Right. So whether the size of the atom down the group, whether it increases or decreases. So across the period, so atomic size of an atom, whether it increases or decreases. If it is increases, why it is increases. If it is decreases across the period, why it is decreases. Right. So that one we will study today. So here in this one, the lithium atom. First we will go for the lithium atom. Here in this lithium atom, we know the atomic number of lithium, that is 3. So if you go for electron configuration, so that is and 1s2 and 2s1. So it will be containing only the two orbitals, 1s and 2s orbital. So if you go for a sodium atom, that is an 1s2 and 2s2 and 2p6. There are being the 3 orbitals. Right. So 3 orbitals. Like that only. So if you go for here, the size of the atom it will be going on increases. The size of the atom going on increases. Right. So if we go for the rubidium atom, the size of the atom going on down the group atom, so the size of the atom going on increases. Why did it get increases? Because of the addition of new shells. Because of the addition of the new shells. See here. So here it is for the lithium, it will be containing only 1s2 and 2s1. If it become for sodium atom, so in terms of the p orbital, it will become extra. So one more extra orbital get added. So if you come for potassium, so that is an 1s2 and 2s2 and 2p6, 3s2 and 3p5. So again the 2 orbital get added extra. 2 orbitals get added extra. So because of the new orbitals get added, so because of that reason only, so the atomic size going on increases down the group. Down the group atomic size it will be going on the increase of right. So you can take any group. You will take the first group, you will take the second group, you will take in terms of a group 18 halogens. You can take any group. The size of the atom going on increases down the group. Right. So they will ask for examination why how it will be vary down the group atomic size. Right. The atomic size down the group it will be get increases. Right. So why it is increases? Because of the addition of new shells. Because of the addition of the new shells. Right. So one more extra shell get added here. One more extra shell get added here. Because of the addition of new shells, so the size of the atom going on increases. Right. So this will study what about the across the period. What about the across the period? So whether the atomic size, whether it may increases or decreases. Right. So if we go for here, so that is the lithium, up to the lithium. So we go for in terms of here. So that is the beryllium. Lithium and beryllium. Lithium. So in the same period, that is the beryllium, the boron, carbon, the nitrogen, oxygen. Right. So they have been in the same period. Right. This is the second period. Right. So here in this one, so if we go for here, the electron configuration of lithium is nothing but 1s2 and 2s1. Right. So 1s2 and the 2s1. So if we go for here, in this, if we go for beryllium, atomic number is 4. The one more extra electron is added to the same orbital. One more extra electron is added to the same orbital. So that is and 2. Here it is 2s1. Here it is 2s2. Right. Here it is 2s2. If the electron is added to the same orbital, the force of attraction is get increases. The force of attraction get increases. If the force of attraction increases between the nucleus and the outermost shell of electron, right? So the size of the atom going on decrease after. Right, I will tell you one. I will write down one example. So here in this one, just assume. So there are the protons, right? So the nucleus containing protons, right? The nucleus containing the protons. So electrons have been present here. If we add one more electron to the orbit, right? If we add one more electron, So if the one more electron have been added means the force of attraction between the nucleus and the electron again increases. Right. So the force of attraction between the nucleus and the electron again increases. So that's why if the force of attraction is increases, the nucleus that will be attract the outermost shell of electron tightly. Right. So now after that the size get reduces. Right. The size get reduces. Right. If it become from here, that is then 2p1. Right. So here it is 2p in terms of here 2p2. Here it is 2p3. See here. So the p orbital containing 1 electron. So here it is 2 electron. Here it is 3 electron. Here it is 4 electrons. So electron is added to the same orbital. If the electron is added to the same orbital, the force of attraction between the nucleus and outermost shell of electron again increases. Right. So that's why the size of the atom going on reduces across the period. Understood? Right. So in terms of here, so across the period the atomic size going on decreases. In terms of it down the group, the atomic size going on increases. Atomic size going on increases, and across the period atomic size going on decreases. Understood? Right. So we come for what do you mean by atomic size? Right. So what do you mean by atomic size? We'll study. Atomic size are nothing but assume this is a nucleus at the center. So there are some electrons. There are some electrons here. Right. Okay. If it come from here, so obviously electrons are present in the orbital or shells. Right. So there should be some attraction between the positively charged protons and negatively charged electron. There should be some force of attraction. Right. So force of attraction. So this distance we are called, right. So this distance we are called atomic size. This distance we are called atomic size. The distance between the center of the nucleus and outermost shell of electron. This distance we are called atomic size. Right. So what do you mean by atomic size? Atomic size is nothing but the distance between center of the nucleus. The distance between center of the nucleus and outermost shell of electron. Right. So we have to select the outermost shell. The electron which is present in the outermost shell. We have to select that shell. So that distance we are called an atomic size. The distance between the center of the nucleus and outermost shell of electron. That one we are called an atomic size. Right. So here if you come for atomic size, so it has been very difficult to measure. Right. So why it is difficult to measure? Because the isolation of an atom is difficult from other atoms. So these molecules has been some strong force of attraction. It has been very difficult to break that molecule into an atom, and atoms have been highly reactive. Right. So that's why. So it has been very difficult to measure. That's why we will go for the covalent radius. We'll go for the covalent radius. Right. So understand what is atomic size? The distance between the center of the nucleus and outermost shell of electron is called an atomic size. So we won't that we can't study the atomic size because it has been very difficult to measure the atomic size because of what? Because in terms of here, so it is very difficult to isolate an atom from other atoms or molecules. Right. So that's why we have to study the first one, the covalent radius. The covalent radius. The covalent radius. Right. So the covalent radius are nothing but in terms of here, assume we'll consider a molecule. We'll consider a molecule. So this is the nucleus of this atom. This is the nucleus of this atom. Right. So this distance we are called bond length. This distance we are called bond length. This distance we are called bond length. Right. The distance between the two nucleus we are called bond length. The half of the bond length we are called, that is the half of the bond length. Right. So half of the bond length we are called, that is the covalent radius. This half we are called the covalent radius. So the distance between the two nucleus we are called bond length. The half of the bond length we are called covalent radius. Understood? Right. So then what do you mean by covalent radius? Right. So here this is the one half, this is the one covalent radius, this is the one more covalent radius. Understood? Right. So but we can easily measure the bond length of one molecule. We can easily measure the bond length of one molecule. Right. So half of the molecule, half of the bond length is nothing but we will get the covalent radius. Right. So what do you mean by covalent radius? That is the one half of the distance between the nuclei of same element in a molecule is called covalent radius. The one half of the distance between the nuclei of the same atom in a molecule is called covalent radius. This is the one half, this is the another half. Just we have to select only one half. The one half of the distance between the two nuclei of same element in a molecule is called covalent radius. What do you mean by covalent radius? That one half of the distance between two nuclei of covalently bonded atom in a molecule is called the covalent radius. Just assume the covalent radius of the hydrogen molecule. Right. So hydrogen, the molecule, the covalent radius of hydrogen molecule, we know that is 74 picometer. 74 picometer. Right. So that this is nothing but the distance between the two nucleus. That is 74 picometer. The distance between the two nucleus, that is 74 picometer. I want to know the covalent radius now. So one half this we have to be divided by the 2. So then it will become 74 divided by 2. That is in terms of here. And 37 picometer. 37 the picometer. Pico is nothing but 10 to the power of minus 12. Pico is nothing but 10 to the power of minus 12. We are called the picometer. That is about the covalent radius. Right. So the one half of the distance between the two covalently bonded atom in a molecule is called the covalent radius. Understood? Right. So we'll go for one more. So that is the van der Waals radius. We'll go for the second one, the van der Waals radius. That's the P, the van der Waals. The van der Waals radius. So I will give one example. Here in this one van der Waals radius, just we have to consider the two molecules, right? So this is the nucleus of this atom, this is the nucleus of this atom, right? And also the neighboring molecule also being present. Neighboring molecule, right? So assume, so this is nothing but in terms of here. So this one we are called bond length, right? The distance between the two nucleus we are called the bond length. Bond length. This is called bond length, right? So even here this one we are called, this is the exact half we are called, this is van der Waals radius. This is van der Waals radius. Right. So if we come for van der Waals radius, this is the one half, this is the another half. Understood? Right. This is the one half, this is the one half, this is the another half. The one half of the distance between the two nuclei of adjacent identical atom of neighboring molecules is called van der Waals radius. Right. So this is the one half distance, this is another half distance. Right. We have to be consider only one half distance. It is the neighboring adjacent molecule. Adjacent is neighboring molecule. Pakkad molecule ante neighboring molecule. Right. So of identical molecule of neighboring atom, there should be intermolecular force between the two molecules. There should be intermolecular force between the two molecules. Right. So that one we are called van der Waals. It's a weak force. Van der Waals radius. Right. So van der Waals radius anta ಹೇಳಿದಾಗ so it is the one half of the distance between the nuclei of identical atom of neighboring molecules is called van der Waals, the radius. Right. So for example, the van der Waals radius of hydrogen atom, right, that is about in terms of the 240 picometers. So the weak when into molecular force yesterday into molecular force, that is to distance yesterday, that is 240 picometer. If we go for here, so that is half is nothing, but in terms of the 240 divided by 2, that is in terms of the 120 picometers. That is 120 picometer. That is the van der Waals force of hydrogen, the molecule. Understood? Right. So we go for in terms of here. The one more, that is the ionic radius. Ionic radius. The third one. Ionic radius. Where ionic radius are nothing but, so there are some ions, right? So ionic form, it is present in the ionic form. So here in this one, so this will be nothing but an ion. So here electrons have been present here. This is an electron, electron, this is an electron, electron, right? So here for this ion, we have to remove one electron. So it will become to the ionic form, right? Cationic form. So here in this one, so this nucleus has influence upon the last electron up to this electron, right? So it has the capacity to influence its power on the last electron, right? So that influencing power we are called ionic radius. Right. What do you mean by ionic radius? The distance between the nucleus and point up to which the nucleus has influence on its electron cloud. That one we are called so ionic radius. Understood? Right. So for example, if I sit here, right, so I can be in terms of here, so I can see up to in terms of here some about 20 benches students. Right. I can't be after that I can't be see. So I have been influenced only up to 20 benches only, right? So I have been that much of influence to see only the 20 benches of students, right? So that one we are called radius, ionic radius, right? So if it come from here, so this nucleus has influence on this electron only, right? So if it is electron is there, but there is no influence, understood? There is no attraction, there is no force of attraction. So that's why. So we can't be consider this one. We have to consider this one only. So this one we are called an ionic radius. The distance between the center of the nucleus and point up to which the nucleus has influence on its electron cloud is called ionic radius. Right. So this ionic radius, if we come for ionic radius, so just we'll compare this ionic radius with the cations and anions and also the neutral atom. Right, it's been very important. See properly here. We discuss about the ionic radius. So we come from here. For example, the sodium atom. So this sodium atom, the size of the sodium atom is about 154 picometer. The size of the sodium atom is 154 picometer. So after losing electron, it will form Na plus an electron. After losing electron, it is about 95 picometer. 95 picometer. If it be write the electronic configuration, that is an 1s2 and 2s2, 2p6 and 3s1. If it come from here, 1s2, 2s2 and 2p6. After removing electron, it will acquire the configuration of noble gas. That is the neon. Right. So neon configuration after. Before the removing of cation electron, the size is about 154 picometer. After removing the electron, the size has become 95 the picometer. Understood? Right. So the size is going on decreases as compared to the neutral atom. The size of cation is less as compared to the neutral atom. Remember that one? The size of the cation is less as compared to the neutral atom, because after removing the one electron from the neutral atom, right, the force of attraction between the nucleus and outermost shell of electron increases. The effective nuclear charge increases. So that's why the size it will get shrink, the size get reduced, the size get reduced. So that's why, so it will be turned into 154 picometer to 95 picometer after removing the one electron. So that one we are called. So that is the given. The cations has been lesser ionic size as compared to the neutral atom. Right. What about in terms of an anion? What about in terms of an anion? Right. So before that, if we go for in terms of the copper, so that is in Cu plus 1. So here it is in terms of a Cu plus 2. Right. So we'll ask the quantitative what about the increasing order, right? So of their size, that is copper ion, copper plus 2 ion, right? Cupric ions. If we come for this one, so already we people have been know the neutral atom has been larger in size. Neutral atom has been larger in size as compared to the copper ion, and then it has been still larger as compared to the Cu plus 2. Understood? Right. So what about in terms of here? So that is if we go for anions. So this chlorine atom, it will be gain 1 electrons to form the chloride ion. The chlorine atom gain 1 electrons to form the chloride ion. So here it is about in terms of here 91 picometer. 91 picometer. Here it is about 181 picometer. 181 picometer. This is a neutral atom. After adding electron, it forms anion. Right. So the size of this anion has been more as compared to the neutral atom. Remember that one? The size of the anion has been more as compared to the neutral atom. Because if you go write the electronic configuration, that is a 1s2, 2s2, 2p6, 3s2, 3p5, 3p5. Right. So the same thing here. That is a 1s2, 2s2, 2p6, 3s2 and 3p6 atomic number. So it will become 18, right? According to the configuration of argon. After adding the 1 electron to the chlorine atom, right, the force of attraction decreases. The effective nuclear charge decreases. So that's why the size get expand. The size get expand. Right. So that's why the anions have been larger in size as compared to the neutral atom. Right. So if we come from here, so the cations, remember that one, the cations has been smaller in size as compared to the neutral atom. As compared to the neutral atom, this neutral atom is still smaller in size as compared to the anions. This anions has been larger in size as compared to the neutral atom. This neutral atom has been still larger in size as compared to the cations, right? So this is nothing but the size, ionic size, right? One more thing, if we go for this one, so assume here it is an oxygen atom. So here it is an oxygen ion, there is a -1.